Welcome. My name is James Taylor, and I'm going to be talking about a new idea for how to define real numbers. So to set the stage, should first talk about what the other numbers are. So we have our counting numbers, 1, 2, 3, 4, 5. We have an arithmetic with them. We can add them, subtract them, multiply them. Comes out nice. The counting numbers become integers because of the subtraction. So you have negative numbers. You have 0. 1 minus 1 is 0, for example. You got all that. We got some rules with them. Great. And you can think of fundamentally as counting numbers as strokes on the page, and you go from there. So how you count stuff. That's the origin. Now, one thing, so subtraction undoes addition. So then there's multiplication. And we'd like to undo that. So that leads to division. So, 6 divided by 3 is 2, meaning 2 times 3 is 6. And so that's nice and easy, no problem. But now what about 7 divided by 3? Not so nice. So that's 2 1/3. Or we might just say 7/3. Or we might say 2.3333 with 3's repeating, right? So that's a rational number. You have an integer over an integer, and it's precise in that sense. We're not often all that comfortable with figuring out what it actually really is because we're more comfortable with decimals, so we write a decimal version of it. But the fundamental thing which is precise is the rational number, and you can write a decimal version of the rational number somewhat precisely in the sense you can indicate what's repeating, because rational numbers always have decimals that repeat forever. Okay, so all good. You've got arithmetic with all those things, rules, orderings, all that good stuff. Now we get to real numbers. Now, why do we have to care about real numbers? Well, because things happen. So I'll just draw a square here. Side length 1 and 1, and that's fine. Feels like something we could do. I feel like I see tiles all over the place that are got equal size squares, and so you draw the diagonal and you try to measure it, and what you end up with is the square root of 2. Now, of course, square root of 2 is a number that kind of goes on forever, and no repeating cycle. Right? So you can't represent the square root of 2 in terms of a decimal with it completely specified. We just can't do that. And basically this is, so related to the square root of 2 is not a rational number. If it was a rational number, it would have a repeating cycle. If it had a repeating cycle, it would be a rational number. These things are not true. So the square root of 2 is not a rational number. Good. So what is it? Well, we call it an irrational number. Call it, the set of rational and irrationals, the real numbers. But what is it? So the first attempt is infinite decimals. Okay, so that's number one. What's the problem with that? Well, for one thing, you can't write it down. And it feels like it's kind of asking to do that. You also have a problem with arithmetic. You kind of, most of the time you kind of start with arithmetic on the right. And even if you start on the left, which is recommended in my opinion, you still need to be able to carry over. So you change the things to the left as you go to the right. That's just why we like to start on the right, so that we don't have to change things. But, starting on the left, it gives you better information to start with. So anyway, essentially you have this carry problem where you don't really know what's going to happen down the thing. And a amusing thing to just experiment with is 1/9 times 1/9 as 0.1 times 0.1. So you actually write it down, do the computation. So this is a rational number computation. And you just see, so it's very easy because it's just a sum of ones, but the sum of ones is getting longer and longer. And so you can see how a trillion digits down the line, you're changing things a trillion digits. Not trillion, like 12 digits earlier. Moving on from infinite decimals, we have Cauchy sequences. And this would be kind of like saying, oh, okay, so we're talking about the square root of 1. And so we just have the sequence of numbers that are telling us, eventually becomes the square root of 2. And so real numbers would be the sequences. This feels like a generalization of the infinite decimal thing. And on a certain level, it seems nice. However, one of the big things with this is that it's not unique. It's very kind of weird when you're talking about it. And because of this, also, arithmetic is somewhat strange. We also have Dedekind cuts. And this is basically saying, oh, it's the set of all rational numbers where x is less than r. I'll just put that in quotes. So the idea is it's less, you take all the numbers that are less than this real number, and that's the real number. Now, this is not a terrible idea, except, and the great example is the square root of 2, because you can write it in terms of a number you already have. X squared is less than 2. So that's great. For roots, Dedekind cuts, awesome, right? But for something like pi, you don't have that nice form. Now, just a quick thing about what pi is. So if you have this unit circle, and then the circumference will be 2 pi, right? And so we have a lot of different ways of computing pi, and we don't, as far as I know, have a simple mechanism for deciding when something is less than pi, other than having to compute pi out to some amount of precision that tells you that it's past that. Okay, so that's Dedekind cuts. Intervals. So another idea, which goes way, way back, is intervals. Interval sequences. So you have a trapping of the real number in these things, and you're kind of converging on it. And so I draw a square around the unit circle, and I draw a square inside the unit circle. And what we get is, the circumference around the perimeter around the square is 8, and that should be greater than the circumference of the circle, which is, of course, equal to 2 pi, and that should both be greater than 4 times the square root of 2, and the square root of 2, let's just take it as an approximation that it's 7/5. So if I divide by 2, here I get 4 is greater than c is greater than 14/5, which is just a little under 3. So that's our starting approximation. We know that c is between 4 and 14/5. And then the idea is you draw another n-gon around the circle and inside the circle, and you get a better approximation, and now you're shrinking, 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 shrinking. Okay. So this is nice. It has the nice advantage of really saying, okay, this is where we know the number is in. However, there's no unique representation of this. So you, again, have, it's like the Cauchy sequences in that you have all these different representations. It's not really clear. Like, you're saying this is the real number, but this one particular sequence isn't the real number because you can have other interval sequences. And so you kind of have to, like, combine them, and they talk about equivalence classes and so forth, which is all these different sequences, and it gets pretty messy and chaotic. So, my idea is essentially, I call them oracles. Yes or no if it is in the interval. So, you give me an interval of rational numbers, and then I say yes or no, depending on whether or not I, the real number, am in the interval. So, that's what this is. It's equivalent to thinking of all intervals equivalent to kind of all rational intervals that contain the real number. Now again, I'll just put quotes around the contain because we're defining the real number, right? So it's not actually in the interval, but it's this idea that we can say, yes, I am in this interval, or no, and that's how we approach this real number. So it's a thing, it's a concept out there. Square root of 2 is the diagonal of a square. Seems like it exists. Seems like we ought to have some kind of number associated with it. We can't actually write down that number, so we certainly can't measure it to any kind of precision. To perfect precision. You can go as far as you like, theoretically. But we're trying to define what it could be. And so this is the idea. Now, what we'll go over in this series is how this actually works out. So, what do we need to know? So, because we don't actually have the real number, because we're trying to find the real number, we need to have certain properties of the oracles. So there are certain things, you say, okay, let me think about this. What do I want? What do I need to have be true about the answers of this thing? So, like, for example, if it says yes on an interval, so like, the square root of 2, for example, is between 1 and 2, right? So that's a yes. So now, if I come along and I say, well, what about minus 1 to the square root of 2 to 10? Well, should be yes, right? And I don't really need to do any more computations because 1 and 2 are in that interval between minus 1 and 10, and so I know it's got to be in there, right? So that's consistency. So you definitely want your oracles to be consistent. Another thing you want is existence. So some interval is yes. It's really important to have that. Not just because, obviously, if there is no interval that exists, then obviously you don't have the number. But in some of the algorithms we'll talk about for computing a real number, with this thing, you have a starting interval. It's that starting interval that allows everything to work out. So if you have a starting interval and the ability to say yes or no whenever you're given an interval, then you can very rapidly get a good approximation for the real number. And we'll talk about that. Now, there's also properties involving what if the real number is irrational. It's a rational number. Well, so, for example, square root of 4 equals 2, right? So I could be thinking, oh, square root of 4, that's a real number. Let me get up my machine and go through this thing. Well, what needs to be true about our answers? Well, basically we want yes if 2 is in the interval and no otherwise. So we'll call this root it. Only one rational is possible to be a yes. Okay, so that's rooted. And then there's closed, which is if a rational is in every interval, then the real is the rational. So basically the way I formulated it in my paper is I call them singletons, so kind of an interval that's like kind of 2 less than or equal to 2. And I kind of write it as 2, 2, like that. And so this would be a yes. So I can feed in singletons. I can say, is this rational number the actual real number? And it says yes or no. So that's kind of an important feature to be able to have, and that's kind of one of the weaknesses for one of the problems is we don't actually necessarily be able to always know, depending on the definition, as to whether a rational number will be it or not. You may not be able to figure out how to exclude it from any intervals that you're testing, but you may not be able to prove that it is actually a rational number either. So it's just a limitation on what we can do. And it could be a problem. I should say that we consider closed intervals, not open ones. And basically for this reason. I want to be able to have singletons in there, so, I do include the endpoints into these intervals. All right. Now the final property, and with this property, basically I've defined what I want an oracle to satisfy. It takes in these closed intervals, gives you yes or no for each one, and it satisfies these 5 properties. And the separation property is really the key. So far, it's almost like a kind of a background property. It's not driving anything. It's just like, closed is kind of like, hey, it's going to be in there, right? And rooted is actually surprisingly useful in that it kind of says, look, you have to be able to separate rational numbers. But separation really brings us home, and basically it's this. So let's say that and I just like the notation AB. So that means AB, that interval, A comma B, but it could also be like there isn't an ordering implied by this. It's just whatever. And A and B could actually be the same number. Whatever. Don't care. Well, actually here, I guess I do care. They do need to be actually distinct, so we'll just go with A less than B. And the separation property is essentially saying that if C, a rational number, is in AB, particularly that it's not the endpoints, then either CC is yes, so that rational number could be the real number, or AC is yes, BC is no, or AC is no, and BC is yes. So that's what it is. You pick a number inside the interval. You say, are you this real number? It says no. And then you can ask about the other. You can ask about the two intervals that this middle point, or in between point, create it and say, is this yes? Is this no? And the oracle should give you exactly one yes and one no for those questions. Not both yes, not both no, one yes, one no. And that separation is what then allows us to compute the real number as much as we like, because I start with my existing interval and I just keep doing this process over and over again, say taking the midpoint of each interval, and I select one based on what the oracle tells me, and I continue. And so very rapidly, like 2 to the n length, I'm down after n steps of this thing. And yeah, so that's what it is. So that is the basic idea of oracles. We define arithmetic in terms of the intervals. So we do arithmetic with intervals, and then we kind of shrink the input intervals down sufficiently small so the output intervals are small, and we can figure things out from there. We can also order them. So if I have two oracles, and this, I've got an interval over here for one and an interval over here, and they're definitely, separated, then this one will be bigger because its interval representation is bigger than the interval representation of the other one. So that's ordering. My main paper on this, the reals as oracles, goes into detail, and I intend to do a video series going over all those details in video form, because why not? My also hope is to have some videos that kind of go into more exploration of these things that might be more approachable to people who are less mathematically invested but still want to kind of know about this. I do think that this idea solves the problem of what, say, a real number is to people. I'm hopeful that students can understand this and appreciate it. I think a lot of the other methods for real numbers, they're kind of complicated and they're not very satisfying, and so they don't get a lot of people don't really say a lot about real numbers. Norm Wildberger went on a video where he looked at maybe 10 books, both calculus and real analysis books, looking for definitions, these things. And I think mainly he found just Rudin had a definition involving Dedekind cuts, which, was nice. And I certainly referenced some of that work when I wrote up the paper. But my hope is that this is an approach that is actually something you could present to even high school students and say, this is what we're doing. We're trying to figure this out. We're trying to figure out what intervals this thing is so we can make it as small as we need to for usefulness elsewhere. And that's kind of what I'm hoping that this happens. So thanks for listening if you've made it this far, and hope to continue on with this as we flush out what a real number actually is.